Yeah, 202. I don't think we said the answers. So I was going to quickly make sure you got your domain and range correct. And that way people who are not here can also see the answers. Okay, so we did number 1 together. Number 2, this parent function is the square root. It's just been flipped this way. And if you can see, that point is going to help us find our domain and our range. Our domain x values are all negative. So x has to be less than or equal to 0. And our y values look like they start at 1 and then they go upwards. So y has to be greater than or equal to 1. Domain and range are tough. We're still practicing domain and range. So you kind of pretend you're opening up a window. So on the x-axis, my window over here doesn't open. There's nothing over here. All of the function is over here above this x-axis. Number 3, what type of function? Cubic. Cubic looks a little bit different every time it's graphed because depending on what you put after the x cubed, if you have something that just has x cubed, it's going to look like this. But the more things you add after the x cubed, the bumpier it could get. So the more exaggerated those bumps could be, depending on all these other terms. So this is also cubic, or a cube function, and it always has domain and range of all real numbers because it's going forever up and down and it's pushing out to the side forever. Number 4 is name is what? Absolute value. So when we do Matho, I'm going to draw a picture of a graph on the board. You'll have to cross out its name on your bingo sheet. So we're starting to tie the graph to the name. This is absolute value. I'm going to abbreviate. Or you could just write the symbol like absolute value of x. Domain is always all real numbers. It's pushing out side to side. Did anyone write the range? What did you say for the range? Where do those y values go? How low do they go? -2 is the lowest the y value can go. So y has to be greater than or equal to -2. So it's everything above -2. Okay? Number 5, what type of graph is that? It's a linear. Now, domain and range, if you put all real numbers, I would count that correct. Usually a line goes forever in both directions. This was a little bit hard to see because it printed blurry. I meant for it to be an application problem, and see how the x values start at 0, but they go forever in this direction with that arrow. So I meant for x to be greater than or equal to 0, but if you put all real numbers because you thought it went forever, then I would count that correct. And then the range, see how the range also starts at 0 and then goes up? I can't quite read what this was. Something, the world, age, and I can't read what that says. Oh, weight? Is that what that says? Weight in kilograms, maybe? Oh, price, maybe? Oh, okay, so like price per pound or price per kilogram. My scale's too blurry. So I would have said y is greater than or equal to 0, but if you said all real numbers, because this is a line that goes forever, I get it. Same thing kind of on number 6. I meant for this to be an application problem, but if you use the parent domain and range, that's fine. This is exponential. Is it increasing or decreasing? Decreasing, which means as you read the graph from left to right, it's getting lower and lower and lower and lower. So it's decreasing. So the parent function is normally all real numbers and y is above the x-axis. But for this graph, see how these kind of have endpoints here and here? I meant them to go, I can't read that number though. Is that like 200? You think it goes from 0 to 200? I can't tell. So I would have said it goes from like 0 to 200 on the x-axis and whatever this is, 0 to 100 on the y-axis. Oh, actually, doesn't it start more like at 30? Or is that 20? 20? I would have said y is between 20 and 100. But if you said just it's above the x-axis, I would count that. And I would have said what? X goes from 0 to I'm going to think that's 200. I'm not sure. So for application problems, I'll try to make the graph come out a little bit clearer. I think I made it too small on there. But you're trying to squish the graph. Where can I squish the graph between those two endpoints? That's what domain is. See how I'm squishing between here and here? And then I'm squishing the graph on the y-axis between here and here. Okay, so as a group, this warm-up is kind of similar. You're stating the parent function, and then you're trying the domain and range again of these different functions. So take a few minutes together and see if you can do that. If this was the quiz on Friday, could you answer a question? But let's talk through them again. This should have been square root, right? So that's the square root function. It's a sideways half a curve. Let's see, all the x values are what? Less than or equal to 4, and all the y values are greater than or equal to 0. Does that look right for question number 1? Question number 2, kind of trick question here, but it's just a scatter plot. It's not a line, it's not really anything but collected data. And domain, you're just going to list the x values. So you should have listed what? -3, -2, 1, 2, and 5. So those are the distinct x values of each of those points. Then you can list your range, the distinct y values. 1, 2, 3, 4, just -5, -5, 0, 1, and 4. Is that right? 1, 2, 3, 4, 5. I think it's -5. So that's listing distinct values. You can't assume that you can connect the dots. The next one, I would be fine if you called it a linear function or a constant function. Constant is the special name for a horizontal line. Your domain should be all real numbers side to side, and your range is just not at 3, 1, 2, 3. I think we looked. So you could either write 3 or you could write y equals 3. I'm just counting the lines, but I think it's 3. Okay, the next one, cubic or cube. And it gets all real numbers for both domain and range. Goes forever in both directions. What's the name for this 5th one? That's the one that we're going to be focusing on this unit, the quadratic or x squared. All real numbers for domain. Let's see, does the range start at 1? Y is greater than or equal to 1. Sound right? And the last one we're going to focus on today, absolute value. We're going to do the parent graph and learn more about this one today. Let's see. Technically, I should have put arrows here, but domain is all real numbers side to side. Where does it start at? 1, 2, 3. Is that -4? So y is greater than or equal to -4. I think some of you could have gone like 4 for 6 on that. So the goal is by Friday that we're 6 for 6 so that we could get a couple of these right on a quiz. Kind of knowing the names. I'll give you a word bank. So you don't have to memorize all the names, but connecting the picture to the graph. All right, next, I'd like you to take a look at a couple resource pages with me. The one I'd like to look at is the absolute value function. So, absolute value function. Vocabulary word is absolute value. So the function absolute value is y equals the absolute value of x. We're going to talk about what does the graph look like, what's the domain and range. The definition of absolute value is the distance a number is from 0. So the absolute value of 6 is just 6. The absolute value of -17 is 17. So on a number line, how far are you away to get back to 0? Basically, it makes everything positive. The tricky thing that the SAT likes to do, because people are like, oh, it's absolute value, right? So absolute value of 7 is just 7. What is 2 times the absolute value of -3? Do you think? Just 6, because 2 times +3 is 6. What is negative 4 times the absolute value of negative 5? What? Yes, because this becomes positive 5, but you're multiplying by negative 4 on the outside. So the answer would actually be negative 20. And some students are like, uh-oh, I know absolute value is always positive. So they're not going to pick the negative answer. But order of operations, you could still have a negative answer with an absolute value that's in the problem somewhere, right? The only thing that becomes positive is what's inside the absolute value itself. So don't get tricked by that. Okay, so it has something called a vertex at 0, 0. That's kind of the bottom of the graph. And we already talked about its domain is all real numbers, and its range is y is greater than or equal to 0. So all those are facts about absolute value. So I'll give you a second to write those down, and then we're going to fill in a table and a graph. So this is one of the functions you'll have to be able to graph by hand. So just like linear functions, absolute value is one that I want you to be able to graph by hand without using a calculator. All right, so we're going to go our x, y, negative 3, negative 2. I think we can go from negative 3, negative 2, negative 1, 0, 1, 2, and 3 in the table. Can I zoom in on that? So what happens to every single one of these y values? They're just going to be the positive of whatever's over here. So 3, 2, 1, 0, 1, 2, 3, they all get to be positive. And we have to keep practicing how to graph. I got to make a note to myself. We've got to do another scatter plot practice. Scatter plot practice. Hey, how did that eagle come out, Jake? But you're gonna show it to me when it's done, and it's working out. So, scatter plot practice where you got to plot it and make a picture. We'll have to do one of those this week. Okay, so I have to go to negative 3, comma, positive 3 would be here. And then negative 2, comma, positive 2, negative 1, 1, 0, 0, and then it forms a V-shaped graph on the other side. So 1, 1, 2, 2, 3, 3. It's a V through the origin, and then it goes forever in both directions. If I change the steepness, I just change the slope. But the slope is always 1 if it's the parent function. All right, so absolute value, see how the word value has a V? Maybe that can be your clue of what it looks like. Absolute value has a V in the word. I think it's the only parent function that has a V in its name. Is that true? Square root, cube, quadratic, linear, exponential. So yeah, it's the only parent function that has a V as part of its name, if that helps you remember. I'm writing that down as an additional thought because I never thought about that before. V in its name. Maybe next year I'll think about that and say that's a little hint. All right. The other thing I wanted to look at was these transformation rules. So if you look at the page before in the resources, there's nothing to write down. I actually, I've already written the rules for you in the resources just so you wouldn't have to copy them down. But we looked at quadratic functions going right and left. See how this is the page right before where we were? This is like your transformation list. Yeah, one page before where we were, right? Just flip over to the back page and you should see transformation rules in the resources. See, I need to number this like R6 or whatever it is. Okay, so it says once you learn transformation rules, you can apply them to any function. Here's how you go left and right, right? We looked at what this did on our exploration, and this weird thing happens. When we subtract 2, we actually move to the right. When we add 2, we actually move to the left. That's the only tricky one that's opposite what your brain wants to do. The reason that it's opposite, what point is that right there? That is the point 2, 0. What happens when you plug 2 into the original function? 2 minus 2 gives you 0. So when in doubt, check what this point does in the original function, right? This one, here's my vertex here, that's been shifted to the left. What happens when you plug in -2 up here? It gives you 0. So it makes sense that -2, 0 is on this graph, but +2, 0 is on this graph. I just kind of remember it's the opposite of what you think. Because I want minus, right, to go to the left, and I want plus to go to the right in my head. So inside the parentheses, it's kind of this weird world where everything is opposite what you think. That's the hardest rule to get under your belt. All the rest of the rules kind of are intuitive. Like, well, that makes sense. I add 2, I go up 2, right? If you look at your up and down, right, adding 2 or subtracting 2, it makes sense. It goes up or it goes down, right? If I have 4 apples and I add 2, now I have 6 apples, right? So I just went up in how many apples I have. Or I go down by subtracting 9 apples, right? Up or down kind of makes sense. Turn it to the other side. Okay, let's think about these 2 different flips. This negative sign is outside the function, right? So it makes the whole function negative. So I'm just writing this down because that's why it's flipping upside down. It's making that whole function negative. This is inside the function. So guess what it makes negative? Only the x values are negative, right? So if I'm an x value over here, now I'm an x value over here. So it's a flip over the y-axis. Only the x values are negative. Negative x. All the x's flip over to the other side. I think the last 2 kind of make perfect sense, right? It's kind of like slope. This almost has a steeper slope, even though it's a curve, right? So the curve is steeper, and then this has kind of less of a slope. We don't call it slope with quadratics, but it's less steep. So to me, those 2 numbers kind of make sense, right? If the a value is bigger than 1, or if the a value is smaller than 1. So those are your 8 rules. So for a few minutes, I want to see if we can do a little bit of just practicing with those rules before we do a game of Matho. So page 204, where is it? All right, page 204. I'm going to do these transformation rules tomorrow at the beginning, but the back page of 204 has a good kind of matching practice. Like on each of these, something has changed about the original function. So you actually may want to take a picture of the transformation rules from that other page or flip back and forth. Let's do a couple together. So here's my function. 2 things have happened to it. Can you tell me the 2 changes that I would have to make to that function? So the changes you can make are left or right, up or down, flip over the x or y axis, and stretch it or shrink it. So what 2 changes would happen right here? This is just matching the transformation. I'll write them up here for you. Like let's say, maybe I'll just put the transformation rules up here. So this would be left, this would be right, right? So that's one of the changes you can make. This is up, x squared plus 1. This is down, x squared minus 1. So then what are my other ones? This would be a stretch, and this would be a shrink. And then the last one is, what am I missing? Flip. So like negative x squared is a flip over the x-axis, and negative x inside squared would be a flip over the y-axis. Not all of these are quadratic, but the same rule, like see how this is inside the parentheses or, in front of the function. All right, so give me the two things for number 1. Up 6, I heard someone say. What does the 4 do in front of it? So when I change the number, that's one of these two things. Is it making it steeper, stretched, or less steep? Stretched. So let's just write stretch or shrink. Okay, let's do number 2 together. I see two numbers that are or two things that are changing this function, the negative sign and the 3. So what two things change about this function? The 3 is a stretch again, right? Because the 3 is bigger than 1. So I'm stretching. What does the negative sign do? So it's a flip over the x-axis because it's in front of the function without any parentheses, right? So it's a flip over the x-axis, or you could say it's being flipped upside down. Let's do 2 more together, and then you try the rest on this page, kind of looking up at the board. We're going to get good at these by Friday. 2 changes on number 3. So what 2 things are happening? Am I going left or right, and am I going up or down? I'm going opposite of what I think. The x minus 4 is inside that weird parenthesis world. So I'm going right 4, and what's this plus 5 do? Up 5. So without even graphing it, you already have something going on in your head. I know where this graph is going to move to. Right 4 and up 5. All right, what 2 things are happening in number 4? Yep, it's less steep, so I just call that it's shrink. It's less tall. And then a plus 8, up 8. Think you can try it with the people at your table and see if you can, draw an arrow. What is different? For each function, they probably have like maybe 2 things happening to it. On number 5, all you have to say is what that x plus 7 does. And on number 6, all you have to say is what that 3 does. The 2 is not a stretch. 2 to the x is the original function for exponential. So this is inside with x, and this is outside the function. Maybe we should do 5 and 6 just to make sure we have those right. Plus 7. That's actually kind of in parentheses, right? It's a strange world where everything's backwards. So this one actually goes left 7 with that x plus 7. This is adding 3 on the outside of the function. So this is up 3, even though it's kind of written backwards. All right, now you try the rest. Try 7 through 14, and I'm going to put up some answers on the board. I didn't quite finish, maybe just follow along for the answers, but this would go right 3. This would flip over the y-axis because it's inside, so the x's become opposite, and this goes up 7. This is inside the function, so that's left 4 because that's plus inside the function. This and this are 2 different pieces. This would be a stretch, and this would go down 10, right? Outside minus 10. Getting any easier? This goes right by 4 because it's inside the function, and this goes up 8 because it's outside the function. This is outside the function, down 2. So your brain hopefully is starting to recognize no matter what function I'm looking at, this number tells me if I'm going up or down, whether it's a quadratic, a cubic, a square root function. Let's see, this would just shift me up 8, and that's linear, right? My y-intercept shifts up 8. What? And then these 2 on 14, let's see, it flips over the x-axis and stretches it, right? It's linear, but it still would flip a negative slope, and it's making the slope steeper. So even for linear functions, they obey the same transformation rules.